right? So just based off the visual, I think it's pretty clear that if you're close to this point of tangency, then the linear equation is pretty close to the original function, like physically close. Right? It's indistinguishable at the point of tangency, but even for some points around it, it's pretty spot on. Maybe a little wiggle room decimal-wise, but as you work your way further and further away from the point of tangency, you see more and more of a deviation. Unless, of course, the original function is a line itself, in which case it would map directly one on top of the other the whole way. All right. So what we get from this is if we can come up with the equation of a tangent line at a particular point, then we could use the tangent line to approximate values for the given function for any coordinate or any x value that's near that point of tangency. All right. With the idea that as you go further and further away from the point of tangency, you'll lose accuracy, but maybe that's not that big of a deal. Fun fact, this is how the calculator determines things like intersections and maximums, minimums, all the calculus stuff that the calculator does. It's based off of this idea. It's all approximation in nature. Because the calculator, when you ask it to find a derivative at a point, it doesn't actually figure out what the derivative is algebraically. So if you tell it x squared, it doesn't figure out that the derivative is 2x and then do the substitution analytically. What it does is it creates an approximation. All right? So similar conceptually to something like this. In fact, when we learn about Newton's method, you'll see exactly how it figures out things like the zeros of a function. Right? It's all approximate values, which is why sometimes when you're looking for the roots of a particular function, you expect it to be 2, but the calculator says 1.99999, and you're like, well, why doesn't it just say 2? And the calculator is using an approximation technique. It's using a numerical method. Right? So it's giving you its best estimate, and then you would have to know that that's equivalent to 2. Right? So what we're going to do is learn how to take cube roots or any kind of root using differential calculus, which I think is pretty cool. It's a cool application. It also happens to be on the AP exam for some reason. I think this goes under the category of somebody somewhere thought, this would be a fun extension of calculus to really kind of dive into. And then the person sitting right next to that person was like, I get what you're saying, put it on the AP exam. The first person would say, no, fun extension, like exploration, application of calculus, like enjoyment. And the other person is like, yes, question number 3 in the multiple choice. And it's like, no, you missed the point. And so it ends up on the exam all the time. It's always a question. It's always on the non-calculator part of it, even though this is the foundation of every technological application of calculus. So, like, computers base their software off of this idea. So it's all technology, but for some reason you have to do it by hand. I don't know. Anyway, it's not hard, so if that matters for anything. First thing we're going to do is, you guessed it, take the derivative of the given function. I'm going to rewrite the given function though. X to the 1/3. All right, so f prime of x would be 1/3 x to the negative 2/3. Now we're doing this analytically, so let us simplify this just a smidge. All right, because we'll have to plug and chug the numbers by hand. All right, so they're telling us to do this at the x value of 8. All right, so what I'm looking for is f of 8 which is 2, and f prime of 8, which would be 1/12. All right, cube root of 8 is 2, squared is 4, times 3 is 12. All right. So what we get from this is a tangent line equation. Point slope form of a tangent line, y equals m times x minus x sub 1 plus y sub 1, which corresponds to y equals 1/12 x minus 8 plus 2. All right. So this is no different from what we had been doing before. Write the equation of a tangent line. All right. Just in terms of the notation, to distinguish this from the original function, which could also be defined as y equals, we call this the linearized model, L of x instead of y. The formula that you see above has the constant value come first, but that doesn't matter for anything. Addition is commutative. So whether it's this or 2 plus 1/12 x minus 8, it amounts to the same thing. All right. So what we get from this is a linear equation that for values very close to 8 would be a good approximation for the original function. All right. So x in here would correspond to x in here for values close to 8. So we'll see how that plays out, because 8.05 is pretty close to 8. 25 is nowhere near 8. So for one of them, we should get a pretty close approximation. For the other one, not so much. All right, so we would do L of 8.05. So that would amount to 1/12. If I'm plugging an 8.05 in for x, this is going to become 0.05 plus 2. We're looking for an exact value here. Again, non-calculator part of the exam. So 0.05 is the same as 1/20th. So we're talking about 1/12 times 1/20th, which would be 1/240th. So if you want to go the mixed number route, you could say 2 and 1/40th. 2 and 1/240th is what I meant to say. Which is actually a pretty good way of writing it, as opposed to the improper fraction, because if I'm going to get an estimate of this, the calculator, is going to come into play. I'm going to do the cube root of 8.05. It's not going to give me an exact value. It's going to give me 2 point something. All right, so this is the 1/240th is going to be the approximation of the point something. So the cube root of 8, so math option 4, 8.05 is what I actually wanted, is that, all right? 2 and 1/40th, that, I keep saying the wrong thing, plus 1/240th. Of course. All right, so it does that too. Yeah, I gotta do it. I gotta do it the old-fashioned way. That. Because if I use the fraction tool, all it does is simplify. Whatever. Either way, but you could say one of them is my approximation, and the other is what it really is. And you can see they're very close to one another. If I had a value that was even closer to 8 than 0.05 units away, then I'd have an even closer approximation. Right? Now, if I do the same thing with 25, it's not even going to be close. All right? So (1/12) times, that would be 17. Plus 2. Is that 3 and 5/12? 17/12 is 1 and 5/12, right? I think. All right, so 3 and 5/12 is what the cube root of 25 approximates to in this, or using this approach. All right, right? So calculator tells us it's about 2.92. We just got a little bit less than 3.5. All right, so definitely lose some accuracy as you move further and further away. When we learn about integration, you're going to see that we can take little tiny distances, even with a little tiny bit of variation from in terms of accuracy. We can take little tiny distances and accumulate those results, and then actually shift our A value over, and then accumulate another tiny distance. And so in the end, we can use polynomial functions, linear functions, to approximate more complicated curves, right? So with polynomials, it would be more appropriate depending on the nature of the curve. So you'll see how we can take, for example, a trig function and write it as a polynomial function. It's a really weird thing to think about, right? But it's one of those approaches where you have to learn how to take derivatives and antiderivatives, work with summations and things like that in order to understand how you could make that transition to begin with. Because part of you would have to be wondering, if we could have written a trig function as a polynomial function all this time, why the hell are we learning about trig functions? Couldn't we just use polynomial functions? I mean, polynomial functions, power functions, those are really easy to work with calculus-wise. So wouldn't that be the way to go? Unfortunately, you have to learn all this stuff in order to understand why that works the way it does. All right, but this is kind of the bridge to that. And also it's the bridge between derivatives and antiderivatives, all right, which we're going to get to in the next unit. All right, so second example, determine a linear approximation for sine of theta at theta equals 0. All right, so we're looking at f of theta is equal to the sine of theta. I need f prime of theta, got a lag here, which would be what? Cosine of theta. I need f of 0 and f prime of 0. All right, because that's our given value. Essentially just writing the tangent line equation. Right, so it's the sine of 0. Cosine of 0? Indeed. So we're looking at L of x. If I want to just kind of cut to the chase a little bit, I'm writing my tangent line equation, except instead of saying y equals, I'm writing L of x equals. All right, so I have my slope, which is 1. X minus 0 plus 0. You wouldn't have to write this if you realize that it's just L of x equals x. All right, and what that's telling us is that for a sine wave, for values close to 0, we can approximate using the line y equals x, a linear function. All right, again, for a trig function, we can approximate it using a linear function. What would you rather work with, a trig function or a linear function? Linear functions, those are easier to work with. So anytime you can get away with that as an approximation, that's the way to go. All right, so just visually, I don't have to break this out on the calculator. Let me just do a quick sine wave. And all right, so they're talking about the point at 0. And what they're saying here, based on the tangent line, here's my tangent line. For the values that surround 0, we can use the line y equals x as an approximate form. So you can test that out pretty easily. Let's say I wanted to find, for example, the sine, instead of 0, the sine of 0.2. Pretty close to 0. Make sure I'm in the right mode. It's around 0.2. Right? It's the model, like whatever x is, y is going to be the same thing. And that's what happened here. Right? If I wanted the sine of 0.7, we sacrifice a little bit of accuracy. If I get out to sine of, let's say, 1 radian, even more accuracy is sacrificed. So the further you move away from whatever your point of tangency is, the less accurate your result is going to be.